So the form of refraction that you all are probably most familiar with are lenses. And so when we talk about lenses in this class, we're going to focus on sort of a particular type of lens that's sort of a simplified version of what you might see in someone's eyeglasses. But what those lenses are is they're devices that focus light by using refraction. So the light comes into the lens and bends. So lenses use the refraction of light to form an image. There's two types of lenses. The first one we'll refer to as a converging lens. And so here we've set up a situation where we have a light source that's infinitely far away so that the light rays are coming into the lens parallel. And so there are a couple important lines that we're going to keep track of. One, of course, is the line of the lens, and we're going to tend to draw that so that the lens is oriented vertically in our pictures. There's also the primary or principal axis that runs horizontally that basically centers our picture about the lens. And so what you see is all of our light rays are initially coming in parallel to the principal axis. They hit the lens, bend due to refraction as they come through. If they entered as parallel rays, they will all end up converging on this focal point. So notice there are two focal points for each lens, one on each side. The focal length is the distance from the lens to the focal point. And so there's a focal length that we could measure on each side of the lens. With a converging lens, what we'll see is this focal point over here on the opposite side from where the light comes in is the important one because that's where the light is going to focus so that all those rays intersect. The other type of lens we could look at is a diverging lens. So same scenario, right? We've got our principal axis, we've got our lens, we have parallel rays coming in from a light source that's infinitely far away. But now when these rays come in and hit the lens, as they refract, instead of bending towards the far focal point, they're going to bend away from the lens using the near focal point. So you'll see that each of these rays can be projected back to the focal point on the same side of the lens as the light comes in. And so that means that as the light goes through the lens, if all those rays are being emitted from this same point, then they're going to diverge on the far side. Diverging lens, just like our converging lens, again, there are two focal points, and that distance from the lens to the focal point still defines the focal length. What is important in differentiating between a diverging lens and a converging lens is whether that focal length is given as a positive value or a negative value. So if the focal length of your lens is positive, then you have a converging lens. Converging lenses are also known as convex lenses. On the other hand, if the focal length is negative, then you have a diverging lens. And diverging lenses are also referred to as concave lenses. So the first sign convention that we're going to deal with, and there will be a series of these where we're going to have to keep track of the signs for these various distances and lengths that we're going to measure. Our first sign convention says that the sign of the focal length will tell us what type of lens we have. So our initial picture was just looking at our two types of lenses and letting light come in from infinitely far away. Now let's see how these lenses will form images of an object. So now we have an object, and again, it's not infinitely far away. Here we have a converging lens, or we could call it a convex lens, which means it has a positive focal length. And as you can see, given our setup here, it forms an image over on this side of the lens. So what are the distances that we're going to want to pay attention to when working these lens problems? Well, the first one we've talked about, that's the focal length. And that's the distance from the lens to the focal point. And for this lens, because it's a converging lens, that focal length will be given as positive. There are two additional horizontal distances that we're going to care about. The first is the object distance. So it's the distance from the lens to the object. The second one is the distance from the lens to the image. So we have an object distance that we're going to use S to describe. we have an image distance that we're going to use S prime. Again, notice that all three of these lengths are horizontal lengths defined from the lens. So from the lens to the focal point, from the lens to the object, from the lens to the image. The two other distances that we'll be interested in are vertical distances. And so these will be distances measured from the principal axis. So we can talk about the object height, how far above the principal axis does the object go, and we can talk about the image height. So how far away from the principal axis does the image go? Again, we're going to use H for these two heights. The unprimed will be the object height, the primed will be the image height. If we switch our lens, so now we have a diverging lens, or again we can refer to that as concave, because the easiest way to think about this is that this lens caves in on itself. It's thin in the middle, thick on the outsides as it's caving in. And so we want to identify those same five distances. Well, again, the focal length we've already talked about. Distance from the lens to the focal point, and because this is a diverging or concave lens, that focal length will be given as negative in this case. We still have our two horizontal distances, so from the lens to the object for the object distance, and from the lens to the image for the image distance. And then we still have our two vertical distances, so the object height and the image height. And so these five quantities, these five lengths, focal length, object distance, image distance, object height, image height, these are basically the parameters that we're going to play with in working these lens problems. Now, as we saw, there is a sine convention that lets us know what type of lens we have based on the sine of the focal length. There are also sine conventions for those other distances. So let's look at a basic setup where we've got light rays originating, coming in from the left. Our lens, again, is oriented vertically, so it's sitting out here along this line. The principal axis is this red line, right? So the blue line is the line of the lens, the red line is the principal axis, and the light rays are going to exit off to the right. In terms of sine conventions, the first one we'll talk about is for the object distance. So we think of the side where the light comes in as the object side of the lens. If our object is over here on the left, meaning on the side where the light rays are originating, then the object distance needs to be given as positive. So our sine convention there is that objects over here will have a positive object distance. If your object is over here for whatever reason, and again, as a general rule, if you just have a single lens, that wouldn't be the way you'd set them up. But as you start putting lenses together, it is possible to use the image formed by your first lens to be the object of your second lens, and then you can have situations where the object for your lens is sitting over here on the other side, so not the side that the light originates on, but on the side where the light exits. In that case, you would have a negative object distance because it's sitting on what we would think of as the image side of the lens. But of course, for the image, it works just the opposite. So if the side over here where the light originates is the object side of the lens, the side over here where the light exits is the image side of the lens, and so images over here to the right of our lens, so on the side where the light rays go out, they'll have positive image distances because they sit on what we think of as the image side. If your image forms back here on the side where your light rays come into the lens, then you have a negative image distance. So in terms of thinking about what's going on with our two horizontal distances, we have an object side of the lens, an image side of the lens, and so whether your object distance and image distance are positive or negative depends on whether or not your object and image are on the side of the lens where the light comes in or where the light goes out. For vertical distances, it's a little bit easier. So for our two heights, positive heights are simply heights above the principal axis. Negative heights are below the principal axis. And that's true for both the object and the image. So we don't have to sort of flip it around when we think about our heights the way we do when we think about the object and image distances. So let's write all this out then. So what we've said is that you have a positive object distance if the object is on the same side of the lens where the light originates. Again, meaning that the object is on the object side of the lens. Of course, that's negative if the object is on the opposite side of the lens from where the light originates, so the side where the light's going to go out, meaning that your object is now on the image side of the lens. Your image distance is positive, again, if it's on the opposite side of the lens from where the light originates. If it's on the image side of the lens, then you have a positive image distance. If, however, your image is on the same side of the lens where the light originates, so it's on the object side of the lens, then your image distance will be negative. For your heights, both the object and image height are positive if the object and image are above the principal axis. Again, this one's a little bit more straightforward. We don't have to flip things around based on whether we're talking about the object or the image. On the other hand, if the object or the image is below the principal axis, then the object height and image height are negative. So these are the sign conventions that we're going to need to pay attention to make sure that when we work these problems mathematically, everything works out correctly.